chemical reactivity standard at level 2. If you've done the acids and bases at level 1 science, so the 90944, you will find there's actually quite a bit of similarity. The two standards sort of flow on from each other. So if you, hopefully you can all see my shared screen. If you can, somebody can just pop into the chat to say yes or no. Yep, great. Okay, so a few things first of finding help. And the first thing is looking at past papers. So if you just simply Google NZQA and then the standard number of 91166, that's a stand, you can do this for any standard, then you will get to this page, which I'll show you right now. And it's really useful because it gives you the standard and all its variations of the standard, but it also gives you the past papers. So for instance, here is last year's exam paper, or you can have it in Te Reo Māori. And similarly, the 2020, 2019, 2018, 2017 paper. You can also see some exemplars where it's actual student answers. So you can also see how the examiner marked it. And I'll be running these same sessions again just before the November exams, and I'll explain that in more detail. And you can then, of course, get all the assessment schedules. So I really strongly recommend, while you're preparing for the derived grade exams, is go through a past paper, perhaps start from near the bottom and move upwards. So by November, you are doing the final sort of 2021 paper. Because it's very good to see then what is needed for achieved merit or excellence, and you can see then the importance of not leaving out any question or part of a question. Guess if you have to, but try and answer everything, because you could get excellence for question 1A, for instance, but if you left out question 1B, you might land up for that whole question just like for an N1 or an N2 grade. So not very much. But if you had answered, say, guessed some things in part B and you just happen to guess right, particularly when they say, is this reaction exothermic or endothermic? Well, you've got 50% chance of being right. So please guess and say which one, even if you don't know. Because then you could have gone perhaps to an A3 or an A4 just through putting something down. So that's the first thing. The other thing that you do not get in this standard, but you will get in the exam, is the resource booklet. Now, the resource booklet in any series, so it's the same for physics, always is for the first one in the series. So if I change this now from 6.6 to 6.4, which is the first exam paper that you get at level 2, then you will see that they give you a resource booklet. Hopefully you can all see that resource booklet here. I'll make things a little bit bigger. Let me do it on my other thing. Oh, come on. So you can hopefully see it more clearly. Okay, so if I show you the resource booklet, okay, that's the standard. Here's the resource booklet. So the resource booklet they give you is just the front page, and then they give you this for the 91164, and you are given these equations to refer to for the 91166. So please use it. And you're also given a periodic table. So the periodic table is not that important for this exam paper. It's more important, say, for the 91164, but definitely use these equations. So you hopefully will be able to work out the pH, or if given the pH, work out the hydrogen ion concentration. Okay, so what we're going to just do now for the rest of the time really is go through a past paper. But actually, before I do that, I am going to just show you another tip that can help. and that's the no brain too small. So if you're doing chemistry or physics, this is a really good website to go to. So if I just click on no brain too small, and it should come up, takes a bit of time. I actually had it already up there as well. So you've got also biology as well. So if you wanted this particular one, I've gone to level 2 chemistry. And then you can look for the 91166 over here. If you're sitting any of the other exams, you can try looking at that. And what this teacher has done, she's a teacher in Whanganui, she has collated, so she's gone some checklists, so we can look at these very quickly. Last minute reactivity reminders, and there are some sort of quick things, as well as what she's done is she's got some extra notes and collated questions. So say you want to really focus on explaining rates of reactions, for instance, you can look at this section, and it's all from the old standard, so in the 2000s, as well as for the standard, all the past NZQA papers collated for rates of reactions, and similarly for equilibria, as well as for acids and bases. So if you're just trying to focus on, like, how do I answer weak acid, weak base type questions, you can just look at that. So here are sort of some of those tick lists. So you can go, it's a bit small, I will say, so let's make it bigger. So you can say, do I know how I can explain the effect of concentration on the rate of reaction, temperature? And as you learn it, tick it off. And hopefully before the exam, everything will be ticked off and you know it. Similarly, this is, as I say, it's just a teacher's way of doing it. I always recommend people doing their own because you learn better, or you remember it more, but it is a good start if you want to get some sort of ideas. So any questions on that, where to get some resources to help you with your studies on this standard? For those of you that don't know where the chat function is, it should be at the top of your screen. It's the second from the left to me. Okay, let's now look at the standard. So pretty much there are three things you need to know. The rates of reactions, so there'll always be a question on rates. Then there'll always be a question on equilibrium. So calculating equilibrium constant, or the concentration of a reactant or product, or explaining the effect of temperature and concentration and so on. And then there'll be also something about acids and bases. So generally a question on rates, a question on equilibria, and a question on acids and bases, although that's normally a little bit on the small side. So the equilibria tends to be like 1.5 of the questions. Just be very careful, and that's why I've got this up. Notice how we've got the same sort of thing coming up. If I just go over here, you've got concentration and rates and temperature and surface area and catalyst. Okay, you've got the same sort of thing here, the temperature, the concentration, and the addition of a catalyst. Those are the same things that come up. So make sure you don't get muddled between them. Or if you're given a reaction, know that if you change the concentration, you're going to be affecting both the rate of reaction as well as the equilibrium position of that reaction. Or if you're changing the catalyst, or if you're adding a catalyst, you're affecting the rate. And hopefully, you know, if you add a catalyst to something, a reaction, it's not going to actually affect the equilibrium at all. Okay, so that's a bit of a trick thing. The addition of a catalyst does not affect the equilibrium system. It just makes it reach equilibrium faster if it wasn't at equilibrium before. And then you've got a new one here of, I'll just change this color to a surface area that you've got to explain for rates, and then pressure. So when you do pressure, it's the same sort of ideas as concentration. Right, so that's the main thing to be aware of when you're looking at the rates versus equilibrium. So let's look at these by going through a past paper, and as I go through it, I'll be saying those key things. So this is from the 2017 paper, if you want to look it up later. Okay, so pretty much we're saying I've got an acid and it's a pH of 4.2. So it's going to be a weak acid because it's not a pH of 1 or 0. I mean, you can get very dilute strong acids that can have a pH of 4.2, but for these sort of questions, it'll be a weak acid. So it's going to be not fully dissociated. So you must use an equilibrium arrow. In this case, they've given you the equilibrium arrow, but if they were asking you, say, in the derived grade exam, and you had to write this equation, make sure you use an equilibrium arrow. So pretty much what's happening here, what does an acid do? An acid is a proton donor. So it's this proton that's going to get donated to the water. So I'm going to have C2H5COO minus plus H3O plus. And it's not going to be affected whether you put in the aqueous or not. Okay, if you want to show off, add an aqueous, but it's not going to be vital. So remember to always do a charge balance. So this was neutral and that's neutral. So overall, this is neutral. So here, if I've got a negative on this side, then I must have a positive to balance my negative. So overall, this is all neutral. So it's very common for a student just to leave out a charge, or actually even to leave out both charges. So just be careful of that. So now you've got to explain in terms of proton transfer. So you just simply have to say what has donated. And of course, because it's an equilibrium, it can go backwards. So if this is my acid, because it's donated a proton, then the conjugate base is what's left when the proton has been taken off, because this conjugate base can pick up a proton and form the acid again. And similarly, this was the base because it accepted the proton, and therefore once it's accepted the proton, then it forms its conjugate acid. So if you don't like writing a lot, you might just want to simply say acid equals C2H5COOH, conjugate base equals C2H5COO minus, and then base equals H2O, and conjugate acid is equal to H3O plus. Okay, and now you would have to say, because you have to explain the proton transfer. I'm not going to write it all out because we're going to run out of time with all my scribbly writing, but you would have to say that the acid is a proton donor and it's donated its proton to the water, which is now a proton acceptor. And therefore it's a base. And once the acid has donated a proton, it's left with a C2H5COO minus, which is the conjugate base. So this would just be an achieved merit level question and not more than that. Please jump into the chat if you've got any questions. Now we're told it's a salt, and when dissolved, it dissociates into ions. So a salt will always break up completely into its ions. So remember, when something is ionic, we've got a metal cation and a non-metal anion. So if you're not sure, so I mean to write cation here. If you're not sure where to break it, look for the metal part, and that'll be the cation. There are some exceptions, and this is the main exception of ammonium. That's a non-metal, but that forms a cation. But apart from that, if you get given any salt and you're not sure where to break it, that is the metal, the cation. But hopefully you would have also seen from the above reaction further up is you had that, oh, actually there was C2H5, hey, but hopefully you might have seen that the anion stops there with the OO minus. So here, because it dissociates completely into its ions, you need to make sure you use the right arrow, which is a go to completion arrow. So I've got the CH3COO minus plus Na plus. So all my sodium ethanoate has disappeared now, for want of a better word. It's all gone because it's now been transformed into ethanoate ions and sodium ions. Now, sodium ions won't react further with water. They just sit there with water and they don't do anything. Sodium ions in solution are always spectator ions. But the ethanoate ions will react further because this is actually a conjugate base of a weak acid. This is the 2017 exam paper. So 2017. Right, so I need to pick this one, and this is going to react further. And now, because this is a hydrolysis, you must have the equilibrium. You will be marked wrong if you do have the wrong arrows. So if you had them both just straightforward arrows or both equilibrium arrows, you know, that is wrong. So now we simply make this accept a proton, because remember this is a conjugate base, so it accepts a proton. So it's CH3COO minus. And if I remove an H from H2O, I'm left with, sorry, I made a mistake. I didn't make it accept that proton, and OH minus. And the reason why I picked up that mistake is I was already doing in my head the charge balance. And I knew I only had one negative charge on this side. And if I had left the negative charge there and then written another negative charge, I would have had two negative charges here. So I knew immediately that something was going to be wrong. And it was because I didn't put in my H. Okay, so now I've got one negative charge in total on this side, one negative charge in total on that side. My atoms do balance, 2 carbons on each side, 5 hydrogens on each side, and 3 oxygens on each side. And now the final thing is always go back to the question and see, have you answered every part of the question? So I have done my 2 relevant equations, tick and tick. I haven't done any explaining yet, and I haven't said whether it's acidic or basic. So hopefully you can work out what it is. If I've got any OH minus present, it must be basic. I hope you realize. So you'd say CH3COO is basic because OH minus is formed by the hydrolysis of the CH3COO minus ion. So I've now ticked all the boxes. I've said it's basic, and I've explained why. Okay, right, yep. And I'll record and I'll be sending out the link. Okay, so any questions with that? You know, let me know if you're not sure about something. Okay, right. Now here, what I've done here, I have grabbed the stuff from the resource booklet, because don't try and do an equation without at least referring to the resource booklet, because you don't want to make a stupid mistake just because you might have forgotten the equation. So always look at the resource booklet when you're doing the calculation. Okay, so pretty much what they're saying here is you've got a pH of 11.6. Oh, sorry. So that's my pH of 11.6. Now that is the concentration of H plus. Okay. And I've got a, well, H plus or H3O plus. Strictly speaking, it's H3O plus. Okay. And you've got to also calculate the hydrogen ion concentration and the hydroxide ion concentration. So if we are told that it's 11.6 for the H plus, and we need to calculate then the hydronium ion, so we just simply need to use this formula because that has got the pH. Okay, I mean, that's also got pH in it, but to use this formula, I have to do this one. So basically H3O plus is equal to 10 to the negative pH, which is equal to, and now you do your calculator. I'll just use the computer one here. So pretty much, let me just dump it over here. You're going to have the entry log, so it's going to be 11 point. I'm used to my old calculator that I used at uni. So it's 11.6, and I've got to make it negative, so plus minus, and then 10 to the x. So that is rather tiny. You probably can't read that. Whoops. So it's 2.5 times 10 to the negative 12. Now it's got a lot of numbers there, but we're just going to keep them in the calculator. And we're just going to make it 2.5 times 10 to the negative 12. Now, whenever you do a calculation, always ask yourself three things. The first thing is, have I got the right number of figures in terms of significant figures? Like you don't want to write 2.511, blah, 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 blah. You're going to round it off. Now, these numbers were given to 3 figures. They are not strict with the pH numbers simply because pH has got its own significant figure rules. So 2.5 will be accepted, or you could say 2.51. Both of those will be accepted. The second thing you ask yourself is, does this thing have units? So concentration of, square brackets means concentration of, so you need units. And hopefully you know the units will always be moles per liter. Okay. And the last thing is, you ask yourself, is my answer sensible? Now, if you know your pH scale, 11, the number in front of the dot, means more or less how many zeros you've got in the whole number if you were converting it to a normal number. So that 11 there needs to be very close to the number that's going to be raised by. So here it's 2.51 times 10 to the negative 12. That's very close to 11, 11.6. So this looks as though I've got the right number. I haven't put the wrong thing into my calculator and so on. Okay, so now to do the OH, there are a variety of different ways you can do it. You could go, now that we have that, we could just simply say it's 10 to the minus 14, because if we look at this one over here, that equation, if Kw is 1 times 10 to the 14 and it's that times that, then OH minus is equal to 10 to the minus 14 divided by H plus. So it's divided by 2.51 times 10 to the minus 12. So if we did this now, if I'm losing anybody, just let me know and I'll try and explain back. So I'm going to just put that into memory, and then I'm just going to go 1 exponential 14 negative, okay, so that's my 10 to the negative 14, divided by my recall memory, which is that big number. Notice how I've kept everything in my calculator. Don't round off until the very, very end. And so I get a number of 0.00398, or I could just use that FE button, and that puts it into scientific notation. So that gives me an answer of 3.98 times 10 to the minus 3. Moles per liter. So remember, how many numbers, significant figures, have I got a unit? Is my answer sensible? And yes, because it's 10 to the minus 3, and you know it goes up to 14. So it's round about 11 to 14, between 3 and 4. So that sounds sensible. So do you think you would have been able to do that? The other way you could have done the OH, you could have said pH plus POH is equal to 14. So in other words, the log of this time plus the log of that is equal to the log of that. So therefore, OH minus is equal to 10 to the negative POH, which would be equal to 10 to the negative, you would just say 14.6 subtract, 14, sorry, 14 subtract 11.6. And then that would have spat out an answer like that. So if you prefer to sort of not keep things in your calculator and start from scratch, you just say 14 subtract 11.6, do the negative antilog, and you'll get the answer of 3.98. Does anybody prefer doing this method of using pH plus POH, or do you always use this one up here? Not sure? I don't want to put you on the spot. Okay, right. So I'm going to drag this down again to our next one. And we're going to calculate the pH of a 2.96 times 10 to the minus 4 mole per liter solution. And it's for potassium hydroxide. So do I have any H plus directly from KOH? Can you see like H plus and KOH, or is that going to be hydroxide? So what we're going to be doing now is we first will be looking at the hydroxide calculation, because when I put KOH into water, it breaks up completely into K plus OH minus ions. So there's no hydronium ions here. The hydronium ions come from the water. So I first need to work out the hydroxide ions and then work out the pH. So to get started is, you can say, I don't like it when they say pH is equal to, because it sort of limits me the way I want to think. So you could say that the OH minus concentration is going to be 2.96 times 10 to the minus 4 moles per liter. And I know that because we are told this is the concentration of KOH. And can you see, for every 1 KOH, I get 1 OH minus. So, it's if I've got one of this, I've got one of that. So if I've got 2.96 of this, it'll be 2.96 of that. So because I know that, and so I know this bit, and I know KW, can you see I can work out H3O plus? So H3O plus is going to be equal to KW, which is 10 to the minus 14, KW over OH minus, which is what we worked out there. So if I get my calculator back up again, it's going to be, I'm just going to clear that. It's going to be 1 exponential 14 negative divided by 2.96 exponential 4 negative equals 2. So can you see we've got 3.378, 3 blah blah times 10 to the negative 11. So we're going to keep all the figures in the calculator, but we're going to round it off to 3.38. So that's going to be 3.38 times 10 to the negative 11. Now again, you ask yourself, is my answer sensible? And yes, we expect to have very, very little hydronium ions present in a basic solution. Okay, if I was trying to work out for hydrochloric acid, then this would be a very weird result. But we've got a basic solution. So having just a tiny, teensy weensy bit of acid present is what I would expect. So now that I've got that, now I work out my pH and I use this equation. So can you see how easy it is if you refer to the resource booklet and you just simply see what have I got, what don't I have, which equation do I pick? So now we go pH is equal to negative log of the H3O plus. So I've kept that number in my calculator. So now I just simply go log. And you get a number of negative, but that's okay. We get rid of the negative of that, which gives me 1.047 blah, blah, blah. Now, if you try doing this by rounding off all your numbers all the way through, you could get quite a different answer here. So keep all the figures in your calculator, and I would round this to 1.05 because the 7 is bigger than 5 or bigger, so it'll make the 4 go up to 5. So that is going to be a pH of 1.05. Now, do we have a unit for pH? Hopefully you know, because remember I said whenever you do a calculation, you ask yourself, have I got the right number of significant figures? Have I got a unit? And is my answer sensible? And I did something wrong actually, because my answer is not sensible. I cannot have a pH of 1 for a basic solution. I did not do something. Can you see what I did wrong? It's not 1.05. Can you see it's probably too small to see. I'm going to get rid of the FE. It's 10.47. Okay, so just by asking myself, is the answer sensible? I've picked up an error that I had my answer perfectly correct. I just simply didn't read the calculator properly. So always ask yourself, is my answer sensible? And the answer would be 10.5 for a pH. So I'm going to rub that out and go, oh dear, but at least I managed to pick it up because I saw that my answer would be a bit ridiculous saying I've got a pH of 1 for a basic solution. Because obviously for a basic solution, it has to be bigger than 7. So pH of 1 would be incorrect. So any questions with that sort of calculation? Nope. Okay. Right. Hopefully I haven't confused you with that error, but in a way it's good that I did that error because you can see then how easy it is to make a mistake. Even though you had everything perfectly correct, you just simply did not read your calculator correctly. Now we've got solutions of ammonia and sodium carbonate, and we're told they are both basic, but they have got different electrical conductivity. So the difference is, you've got to say, is it a strong acid? I mean, I know they're basic, so it won't be that. A weak acid, a strong base, a weak base or a salt. Okay, now strong acid will always have lots of H+, and so it'll always have a low pH, and it'll always have a high conductivity, because, and this is what you've always got to write about when you've got to talk about conductivity. What is an electrical conductivity? It's when you've got moving charges. You know how many charges can move between 2 points per second. So if you've got lots of charges able to move, then you're going to have a high conductivity, electrical conductivity. If you have just a low concentration of charged particles, then it's going to be not a very good electrical conductor. Now, weak acid doesn't have very much H+. Okay, so this, how can I make this? Lots. So I'll just say here lots. And this is little H+. So it's still got H+, but so it's going to be a pH below 7, but nowhere near like 1 or 0 or 2 even. Well, maybe 2. But it'll have a pH between, let's make it between 2 and 6. Just for, so it's going to be below 7 and it's normally above 2. But it will have a low conductivity. And the reason is it doesn't have much or many ions in solution. So if there aren't any charged particles there or very few, it's not going to conduct. Strong base is going to be like a strong acid, except it's going to have lots of OH minus. So it's going to be the opposite of a low pH. It'll be a high pH. But it will also have a high conductivity for the same reason as a conductivity, because it's got lots of OH minus present. Weak base is going to be similar to a weak acid in terms of a low conductivity, because we've only got a little bit of OH minus present. Okay, and there are no other ions there. And it's got a pH of above 7, but usually to about, what would we say, 12. Okay, and then our salt. A salt is something that will dissociate completely into its ions. So it has a high conductivity. But depending on the type of salt, it could be neutral, like NaCl, or it could be basic, like the salt they've given you here. I mean, a carbonate's not really a salt, but it is a type of it. Or it could be slightly acidic. So it does depend on the type of salt. So let's now explain with all of that. And the best way to do it is really through equations. So, and now you've got to use your arrows to say whether you're going to get lots or little. So for ammonia, you've got NH3, and when you put it into a solution, you're going to have a little bit of that ammonia forming ammonium and OH minus. So if it's only a little bit, then are we going to have lots of these ions, or are we going to have mainly neutral particles? So hopefully you can see if only a little bit of this reacts with water, then it's going to be mainly this. So we're going to have a low conductivity because we don't have very many ions present. It's mainly all these neutral NH3 and water molecules. Now, we're not told to discuss the pH, so we're not going to go there. Then the other one is the Na2CO3. So what happens with this one is it goes completely, a salt always dissolves completely. So we're going to have 2 Na plus CO3 minus, 2 minus, sorry. So hopefully you can do that. You can see there's my salt. I'm going to have a metal cation. And please don't say Na2 cation, it's Na plus. So I've got 2 of them. And I've got my anion. So you just look for the metal part is the cation. The non-metal part over here is the anion. Now, I've obviously got lots of ions in solution because I've got none of this left. That's gone completely into Na plus and CO3 2 minus. So I'm going to have lots of ions in solution that are able to carry a current. So this will be a high conductivity. Now that's really all what they asked for. They just asked for the electrical conductivity. They did mention that this was basic. So you might go, why is this basic? So you could, if you wanted to, write a hydrolysis equation. So a tiny bit of this is going to react with water, just like ammonia. So a tiny bit. So use your equilibrium arrow, and that is going to then form H, the hydrogen carbonate, plus OH minus. So can you see a hydrogen from H2O has joined? So this is now an acid because it's donated a proton to this base to form the HCO3 minus and the OH minus. So you can see it's basic because I've got a bit of OH minus and a bit of OH minus there. Any questions on that? I really, really, really strongly recommend that you use equations. And if you like, number your equations 1, 2, 3, and then refer to equation 1 or equation 2 in your explanation. But just they say a picture is 1,000 words. Equations in chemistry are like 1,000 words. Because once you've got that equation, you can see, okay, I've got mainly this present and very little of that. So here you could say in equation 1, the equilibrium lies to the left. So we've got mainly neutral molecules, very few ions present. So it's a low conductivity. And we need, always state what conductivity means. So that conductivity is when you've got charges able to move. But here in equation 2, the reaction goes to completion. So I've only got ions in solution, and therefore I've got a high conductivity because I've got lots of ions. And then if you like, you could say some of that carbonate does react with water to form more, ions like this, which really actually increases the conductivity because I'm actually making out of that one ion of CO3 2 minus, I'm actually making 2 ions out of that. So I've got even more conducting species. Okay, right, we've got 1/4 of an hour left. And we haven't even hit question 2 yet, so let's go a bit faster. This addition of a small amount of iron helps speed things up. Okay, so any rate question, the key word here is frequency of collisions. Okay, and always use something to do with rate as per unit time. Because if I said I've got a road on my right-hand side that has 2 collisions and the road on my left has got 10 collisions, you would think that the road on my left is more dangerous. But if I said the road on my right has got 2 collisions per week and the road on my right has got 10 collisions per year, you'll change your mind and you'll say the one on the right is more dangerous. So that's why that frequency of collisions or the number of collisions per unit time is so important. Don't just say there are more collisions because 10 is more than 2, but it's per unit time, like 2 per week or 10 per year. So make sure you always, you're definitely not going to get merit to excellence if you don't refer to frequency. And I notice actually sometimes they want it even for achieved. So hopefully you would have worked out that this is a catalyst. And now when it says you may include a diagram, I would always do it. So basically the diagram they want here is you've got energy over this side, you can just call it E, and this is just the reaction coordinate, or as the reaction proceeds. Don't say time, just say reaction coordinate. And pretty much you've got your reactants of ammonia and, N2 and H2. And they need, when they collide, they need a certain amount of energy. Now, we don't know whether it's exothermic or endothermic because we're not told. So you can make it like this if you wanted to, but you do need to label it and say that this is the activation energy. They won't mark you wrong if you made this one higher or lower, because you're not told, you're not given anything about that. And when I have a catalyst, then I provide a different pathway which needs less energy. So another key word, apart from frequency, and this works for temperature, for surface area, and for catalyst, is a greater proportion of the collisions are successful. So that is also a nice key thing to remember in your explanations. So basically what you're saying, when I want this reaction to occur, my nitrogen must collide with my hydrogen, and that collision must be hard enough to overcome the activation energy, which is going to enable them to change, so to break those bonds and make new ones into ammonia. So it needs a certain amount of energy, and if the collision doesn't involve that amount of energy, it's not going to be successful. But when I add a catalyst, it provides a different pathway that needs less energy, or it has a lower activation energy. And that means instead of like on average 1 in 100 molecules having enough energy to make the change, when I have a catalyst with a lower one, it's perhaps every 1 in 3 can now have, in that collision, have enough energy to change. And so therefore, because I've got a much greater frequency or a much greater proportion of collisions that are now successful, it's going to be a bigger rate of reaction, or greater rate of reaction. Okay, so all of these are like this. Here, I think this is pretty straightforward, and it's just an achieve level question. Remember, it's always products over reactants, and any little number in front is raised to the power of. Because in a way, I'm saying NH3 times NH3 all over N2 times H2 times H2 times H2. That's really what I'm doing. So don't write that. I'm just explaining the background, but that's why it's NH3. Now in chemistry, we use the square brackets to mean concentration of. So we do have to show the concentration of, that's raised to 2, and then it's N2 H2. And I think though that most people know that sort of thing. Right, let's carry on. Okay, now here we have to work out whether it's an equilibrium. So pretty much you have to do the calculation and see if you land up with an answer of 640. If you don't land up with an answer of 640, then you know it's not an equilibrium. So you've got to do the calculation first before you can circle yes or no. But if you were running out of time, as I said, just guess. Don't don't leave something blank if you can just throw something out there. But you would have to write this down. So you'd have to use what you had before. And so you'd say Kc is equal to NH3 squared all over N2 times H2 cubed. Now you do need to be able to use your calculator. I'm not going to do the calculation, but even if you don't do your calculator, make sure you write at least these sort of things in there. Squared. Now I've changed the square brackets to round brackets because now it's just a number. The N2 is 0.0821 and this is 0.0583 cubed. So you would just simply work that out and then you would just see, is my number equal to 640? If it is an equilibrium because it matches. That's what we're supposed to get. If it's a different number, it means it hasn't reached equilibrium yet. Okay, if you want me to go into more detail, then let me know. Now they say as the temperature increases, the value decreases. So if I had my equation, N2 plus H2 goes to NH3. So, and bearing in mind that Kc is equal to the products over the reactants, that means if it decreases from 640 to this figure, so this is getting smaller, that means that my products must be getting smaller and my reactants must be getting bigger. Hopefully you can see that. So in other words, as I increase my temperature, the equilibrium position is going to shift to the reactants. Okay, now if it's reactants, now you've got to say pretty much why is it going to shift. So I'm going to say, okay, say this was exothermic. That means the heat is being given off. Now, if I increase the heat by Le Chatelier's principle, the equilibrium is going to shift in such a way so as to absorb that change. So if this reaction gives off heat and I'm adding heat, then it's got to use up that heat and it's going to go this way. So the one I guessed first of exothermic, just because I picked it first, can you see that that is correct? Because if it's exothermic, it means heat must be given off. And it means if I increase the temperature, then the reaction is going to try and use that added heat to use it up to make the heat go down again. And it's going to shift to the left. So therefore, this is an exothermic reaction. If I'd picked the other one, if I had said, for instance, just to start off with, oh, what happens if it's an endothermic? So I need heat. So if I'm heating it up, can you see it's going to go more to the right? So I'm actually going to get more products. So it's going to be bigger at the top and smaller at the bottom. So my K will actually get bigger. So hopefully that makes sense. And I hope I haven't lost anybody there. Let me know. It's actually quite hard because I can't see your faces, so I don't know if you're getting it or not, or if you're going, oh, I know all this. Okay, so pretty much you would just explain it in terms of Le Chatelier's principle. Pardon me. First work out, if Kc is getting smaller, it means I must have fewer products and more reactants, and therefore think of which way is it going to shift. It must shift to go to more reactants. And therefore, I've got to use up heat rather than give off heat if I'm heating up the system. Okay, and question 3. 5 minutes for question 3. We're doing very well. Here's now another one about a reaction rate. So this is with the frequency of collisions again. They've actually mixed the equilibrium and the rates questions up quite a bit on this paper. And so it's an acid-base reaction. Right, and they're pretty much saying, okay, we're starting with a big mass, and it's the same mass of whatever we're doing, and we're going to be finishing with the same mass of products, but reaction B, it goes a heck of a lot faster because in a shorter period of time, I have lost a lot more mass. So the reaction is going a lot faster in B. It's a steeper curve. Always refer to the graph as the curve or slope steeper or more or less steep. That's important for your excellence level question because it shows you are interpreting the graph. So it says compare and contrast the reaction between the two things, carbonate and hydrochloric acid at 2 temperatures. So this is the factor that we got to explain. Now temperature, if I can do this in 3 minutes, you've got to look at 2 different things. First of all, you've got to explain what temperature is and then link it to kinetic energy. As the joke goes, kinetic energy is the a thermometer is the speedometer of atoms. So thermometer measures temperature, is the speedometer is how fast they're going. So the higher the temperature, the faster they are going, the greater the kinetic energy. So if I increase the temperature to there, they're moving faster. And if they're moving faster, there's going to be a greater frequency of collisions. If you think of walking around the room and running around the room, you're going to collide more often into things when you're running than when you're walking. And you've got to link it to the kinetic energy. However, the important thing is the activation energy. So just like you spoke with the catalyst, you've got to do the same thing here. Because when they collide, because they're going faster, they hurt themselves more, or there's more energy involved, and therefore they will change more readily because there's more energy involved. So the second one is not only are they going faster, so there are more frequent collisions, but a greater proportion of the collisions are successful. So I always use an example of, say we've got at say 20 degrees, we've got 20 collisions, and I'll make it 100 because it's always easy to start with 100. So it's 100 collisions, but at 40, we've got, because they're moving faster, we have 1,000 collisions. So that's just general collisions. But at 20, only 2% of those are successful because they've quite low key collisions. So I've only got 2 collisions per second that are successful. But when I do that 40 degrees, then I've got perhaps 10% of the collisions are successful. So can you see I go from 2 collisions per second to 100 collisions per second. So can you see how important the second effect is? That if they are the collisions involve more energy, you are going to get a greater proportion of them being successful because they're overcoming the activation energy. Okay, so that's that one. Make sure you speak about both of those things. And finally, we are sort of running out of time. So I think we can just leave it there. You can look at the assessment schedule for 2017 to have a look. Again, just some keywords. Make sure you look at the question. Here you need to talk about the color. Okay, so you've got to say, is it going from blue to pink or pink to blue? And you told it's endothermic. So obviously one of these things are going to be changing the temperature. So you've got to say, is it turning pink or is it turning blue, and why? So you've got to talk in terms of Le Chatelier's principle. So here, for instance, more water is added. So I am increasing this amount. So by Le Chatelier's principle, if I'm adding a stress, the system is going to change to remove that stress. So the equilibrium position is going to shift towards the reactants. It'll shift towards the left. So my solution will turn pink when I add the water. If I was changing the temperature, so let's have a look what they say about the temperature. It's put into ice cold water. So we're going to lower the temperature. So again, it always sort of write heat as a reactant. So if it's endothermic, it means heat is on this side. For endothermic, heat is on this side. For exothermic, heat is on the product side. So if I'm putting it into ice cold water, I'm decreasing the temperature, which means that the reaction system wants to shift to try and increase the temperature. So for both of these cases, it's going to turn pink, because in the second case, I'm trying to get more heat. In the first case, I'm trying to remove the added H2O. So I think that's it from me. I'll put this up onto my YouTube channel, and then I'll send out the link. But hopefully that has been helpful. Let me know if this is what you wanted, if it's been helpful, because obviously I'm trying to do it for you to make sure that, it's useful for you. So was that more or less what you wanted?